It's a great honor to have the opportunity to address you today. Let me begin by thanking you for the time we will share. My name is Woo-Young Moon. I'm from SK in Seoul, Korea. I'll be presenting my paper titled "A Framework of Soft Sensor Systems with Machine Learning." The content of my talk include introduction and process to generate soft sensor model, and development of framework. And I also want to show experiments. And then concluding. Let's start with the introduction of soft sensors. Soft sensor is defined as a soft system, soft component that perform the same functionality as hardware sensors. It's very similar to hardware sensor. Soft sensor are widely used to realize efficient operations in the industry. There are cases though in which some of them cannot be measured online due to the lack of online measurement instruments or environment. As you can see in the left drawing of the example, many variables are monitored through online sensors easily. As you can see in the right drawing of the example, soft sensor can be a solution to these hard-to-measure variables. The design of soft sensors and its software framework are technically challenging, and the key challenges are identified here. By considering the technical challenges addressed above, the development of soft sensor framework requires a high degree of engineering considerations. The generic data model and machine learning schemes need to be realized. And the developed framework needs to conform to the designed architecture. Now let's turn to the topic of process to generate soft sensor model. A process to generate machine learning models for soft sensors is defined by considering the typical machine learning process and the characteristics of soft sensors. The process consists of 4 steps as shown in the pictures, and each step is defined with an input, the output, and instructions. So we defined a process of 4 steps to enable soft sensors. Step 1 is the acquire data set for learning. Step 2, we select features for the soft sensor model. And then we generate the target soft sensor. And finally, we evaluate and maintain the soft sensor model, otherwise go back to step 2. Now, I want to describe acquire data set for learning. The most important first step in designing a soft sensor is to obtain good quality data. Typically, industry data is incomplete and incorrect, containing missing values, noise, outliers. After resolve the missing data issue, we need to normalize the data to make sure that data have the same scale. The data in a sensor-based application database varies in size depending on the unit and process characteristics adopted. The learning accuracy relies on variables with a larger scale than variables with a smaller scale. The methods used in this paper are general methods such as min-max and z-score normalization. I want to explain the second step, select features for the soft sensor model. This step is to select effective features for generating machine learning models. As we can see in the picture, a Pearson correlation coefficient is used to find the relationship between the physical sensor dataset and the target soft sensors. This is for defining a feature set to analyze the relevance of the available physical sensor dataset to the target soft sensors. Variance inflation factor is used to rank the importance of the features. This is for only the datasets that are specific and relevant to target soft sensors are identified. After evaluating their importance with these methods, the incremental feature selection approach is applied to determine the optimal number of features. That brings me to the development of the framework. The functional view, represented with a UML component diagram, is depicted as shown in figure. Sensor data acquirer is to acquire sensor data from data sources. Preprocessor is to obtain and import sensor data, and do pro-processing for learning. Learning engine is to train the model for soft sensor design by applying machine learning algorithms. Adaptive manager is to load components and apply new algorithms to the model operated at runtime. In this presentation, the behavior view is focused on how to design for handling the third technical challenges of developing the framework. Activity diagram A shows select features for soft sensor models. First, the framework gathers pre-processed data set for soft sensor design. Next, second and third, the framework finds relationships between the data sets and calculates their multicollinearity. And finally, the framework ranks the importance of the feature set. This framework allows preprocessor to select features for soft sensors by considering the feature importance. Activity diagram B shows generate soft sensor models. Next sequence diagram will explain the control flow of soft sensor model training and operation. When the framework receives a request for soft sensor design, the framework learns soft sensor models by using machine learning algorithms. When the learning engine trains the models, the model evaluator evaluates the accuracy of models and checks whether online changes are needed or not. If online changes are needed, the framework builds a new model and deploys the model through the provider. If not, it transfers soft sensor estimation results to the operator. We now then to present our extensive experiments and assessment. The purpose of the experiment is to show that the process of the soft sensor is well designed and provides high accuracy. In addition, we aim to examine whether the proposed framework of soft sensors can overcome the technical challenges of the soft sensor. We evaluate the accuracy of a soft sensor with proposed algorithms based on the soft sensor development, to see whether the soft sensor framework can yield better performance. The number of sensors data is 24 physical sensors and 2 lab sampling data. 24 physical sensors data set in the sensor-based application database include measurements of flow meter, level gauge, thermometer, and pressure gauge. The number of sensors data is about 2,544 per physical sensor. The total number of sampling data is about 1,400 per lab sample. As shown in this picture, we utilize conventional approaches to selecting features such as Pearson correlation coefficient. The variance between the physical sensor temp and the lab sampling data is evaluated with the PCC. The selection of most appropriate features is circled based on PCC. The selection of most appropriate features is important by at least 3 reasons. First, the right set of features can yield highly performing machine learning models. Secondly, the right selection of features can also contribute to reducing the complexity of models. It can also lead to the selection of a minimal set of essential soft sensors for a given application. Thirdly, the right selection of the features provides a vital information or indications in choosing the minimal set of essential sensors. It is a well-known fact that using a smaller number of sensors to get the environment status is always better than doing the same work with a larger number of sensors. The VIF measures how much the variance of an estimated coefficient increases if the predictors are correlated. A value of 1 means that the predictor is not correlated with other coefficients. The higher the value, the greater the correlation of the variable with other variables. If the value of greater than 10, the correlation is regarded as very high. Typically, cutoff 5 is also commonly used. If the given VIF value is lower than 5 such as TI006, FIC003, FIC0, and TIC007, we decide to include it in a feature set. If the value is between 5 and 10 such as FIC009, FICFeed, TI004, TI002, and PIC001, we select it as a feature after considering PCC. The online analyzer of the soft sensor framework evaluates the accuracy of the soft sensor prediction results and determines if a model change is needed or not. There exists a variety of different soft sensor models and hence their evaluation metrics could also be various. The result of evaluating soft sensor for chemical processing plants is shown in picture. In the figure, the red line shows the prediction results through the trained RF model. The blue line shows the results of the real target laboratory property. The RMSE of the test data set is 0.289, which is higher than the all data set. However, it can be chosen as a soft sensor model based on the accuracy of the soft sensor. Therefore, the RF can be used as an algorithm for the soft sensor property prediction. The trend of the soft sensor value is consistent with the actual value, as shown in pictures. In other words, soft sensors based on ML models can estimate product quality variables. We could provide reliable quality property data to operators in real time. It allows operators to improve the product quality by tuning the chemical process conditions based on predicted values from the soft sensor. In the figure, the blue line shows the prediction results through the trained model. The red dot shows the results of the real target laboratory property. So now we come to the last part of my presentation. In the future, it is required to review the applicability of the improvement and optimization aspects through expansion and linkage of the estimation model. Next, it is required to secure a methodology for estimating the process/quality changes according to the changes in operating conditions. And finally, we need operation guidelines with case studies for the utilization scenario. Increasing estimation accuracy through continuous data learning and model improvement is essential for practical applications. We believe our work will reduce the cost of developing soft sensor and functional analysis and apply it to all systems that require functional analysis in the industrial sector. Thank you for listening.